Welcome to Breadboarding. In the previous video, I managed to get this add-on board with the two 32K ROMs here. These are EEPROMs, electrically erasable programmable read-only memory. So EEPROM is a lot easier to say. So at the moment, these just have very simple test programming because we don't have any system memory yet. We only have the ROM, so we can't really do very much other than just some basic sort of tests, which I'm going to go through in a minute. So during this video, we're going to be testing out the circuit, making sure that we're getting the right signals from our logic analyzers. At the end of this video, we should be in a position where we can then start to add the 32-bit memory module. So this is video 18 in the 386 Breadboard PC series, and this is the 16-bit EEPROM and x86 assembly language part 2. Now I said there were a couple of things I needed to change. So in fact, I had put in the program or logic device into the circuit, but I'd forgotten to program it. So when I first ran this, it didn't really do very much. So that SROM-A PLD has now been programmed. There's one extra low enable pin that needed to be wired to one of the buffers, and also the low A20 signal, which is one of the signals which is used to disable the memory above 1 megabyte for legacy software. Because after a reset, then in fact this signal is defaulted to high. So I've set this to high, whereas previously I had it tied to 0 volts. So when we do the testing, that's the only real change there. It's probably worthwhile having a quick reminder of what the test program does. Now, if you want to look at the previous video, so an awful lot of this I covered in the previous video. So there's all the background here, the schematic, the test software, the fact that we need to split the code when we assemble it into odd and even bytes, and then wiring up the breadboards and programming the breadboard. So if you want to have a look at that, there will be a link in the top right hand corner of the screen here, which you can go to that, and it will also be in the comments below. There's a very simple test software we have here. To start with, we're just filling the bottom 60K of the two EEPROMs with ascending byte going from 0 to 255, and this little loop here in NASM syntax just populates that area. Then at the very top of the memory map, the Intel processors, when they come out of reset, start at the address FF0. So this would be 4 Fs and a 0. So this is the top of the 1 megabyte address space, and it starts execution just sort of 16 bytes down from the very top. And the first instruction we do here is actually just jump to the test start. And then we just have to initialize some of the segment registers which are needed to talk to the top 64K of the memory map. So this is where our ROM is. All we're doing is we're reading 1 byte from a memory location starting at F0000, and then we just increment the index, compare it to see if we've done 60,000, and then once we have done that, we just halt, we just go around in a loop. So we should just be reading 1 byte at a time, and we would expect to be reading bytes going from 0 up to FF and then from 0 up to FF many times. Now in the previous video we had a look at the output here, so you can see this is the zeros to FF filling up the bottom 60K of the ROM. And we also looked at, this is the file where the even bytes have been split out. So we can see we've just got the even bytes there and the odd bytes, and that's what we use to program the two EEPROMs. And down the end, we can see that we've got a EA00, so this is the jump instruction, and then this is the address in here. Now, when we're looking at the data in logic analyzers, the Intel chips were little endian, and this means that the least significant byte tends to come second. And when looking at this, it can be quite confusing. So what I've done in the logic analyzers, we have all the data like this. So the SD0 to SD15, so this is the 16 bits of data we're getting out of the EEPROMs. But what I have done in here is when I've actually decoding this, rather than putting the least significant byte first and the most significant byte there, I've swapped them around. And all this means is when we're looking at the data on the screen here, it's actually going to match the output that we see here. So when we go to our listing here, for example, we'll see like EA00, F000, F0FF is what we would see. And in fact, when we go back to the binary there, you can see EA00, F000, F0FF. And we should actually see the order in the logic analyzer match this. If we put it the other way around, then we'd have to keep reversing the bytes in our mind. And I must admit, my brain doesn't work in little endian mode. And then this is where the actual test code starts. It starts with B800. So we can see here that we've got B800, F0BB, F0BB. So the order that we're seeing the bytes here in the code will actually match what we see in the logic analyzer. And then what we should be able to see then is, as it goes through reading all the data here, going from 0 up to F and all the way through up to FF, we should then just be able to see the address matching the data byte. And what this allows us to do is ensure that the address lines are actually connected properly, because if we were seeing the address didn't match the data, it would indicate there's a problem with the address lines. So before we go into the test, this were the list of tests that I did in some of the earlier videos. Now I've added a 16-bit EEPROM test. Now in these tests, there are some of these test signals that we had. So for example, the active low memory 32 line we had set to low when we were testing 32-bit access, but high for everything else. So we're going to set that to be high. The 16-bit memory access was actually tied high and low in these tests. Now it's going into the PLD we've just added. So this will be controlled by the ROM PLD. So when we're accessing the ROM, then it will actually set the 16-bit memory access flag. And these other values have also been set. We've now disconnected our dip switches that we were using to set some of the very simple test program bytes on the data bus. And I've also set the low A20 line to high or 5 volts, because that is a default after reset. We just look at the schematic. The low A20 determines whether the LA20 address line is either wired to 0 volts here or wired to the processor address 20. And because on reset this is defaulted to high, I have set this to high rather than low that it was previously. So it should be ready now to run the tests. So we're just going to go into the logic analyzer and set these up. So the LA2016 logic analyzer, so this is 16 input lines. This is pretty much just wired up on the program or logic device. So if we just look at that, this PLD has the latchable address lines plus one of the ISA SA16 address lines. So these are just buffered through the CPU, whereas these are latched from the CPU. And then we have the memory read control line coming in, memory 32 coming in, and then these are the outputs. So the main things that are driving the ROM is we have the ROM chip enable output. We have the ROM enable for the buffers. So this enables the buffer chips so that the data, the ROM data, can go out onto the SD data bus. And we also have the ROM1 output enable, which goes to these two output enables. If we had the other lower 64K of ROM here, then we would use the ROM2 output enable. So this would allow us perhaps to include ROM basic, for example, as one of the options for the boot up. So the logic analyzer here just basically looks at those inputs, the bus or board address latch enable, and these other signals. So we'll be looking at those. And obviously when I ran this the first time, there was no output here, and I realized I'd forgotten to program the PLD. So the PLD has now been programmed. We'll just put this ready to power on. If we look at the other logic analyzer, so this is the 32 channel logic analyzer, and what we've got here is the SD0 to SD15, although we are looking at this with the SD0 to 7 as the first byte and SD8 to 15 as a second byte, which is the opposite way around to which you would normally do this. Then I've also got the lower 8 bits of the SA address bus. So we should see that the address here matches the byte being read from the ROM. Just got the reset so we can have a comparison between the two logic analyzers. So when the system comes out of reset, that will give us a common point. Then we've got some of the control lines coming out of the CPU, the latch control lines, and this actually can be decoded into a number of states. We covered this previously, and what we expect is, to start with, we'll have the value of 4, which is memory code read. So we'd expect then, when we're reading the data from the ROM, to have code 6, which is memory data read. And then eventually when we finish, when it halts, we'd expect to see 5. So we'll check that the values coming out from those control lines match this a little bit later. So we'll just run this and wait for the power to be on. Okay, so I'm just going to switch the power on. You can see the voltages there, about 5 to 4.9 volts. Let's have a look at the logic analyzer traces. Okay, so we can see here that with our reset signal, the processor is held in reset, so an active high reset, for about 350 milliseconds after power on, and then the processor comes out of reset. And we can see here that this is the decoded LA23 to SA16. So this is the kind of upper 8 bits of the 24-bit address here. This gives an upper area of 16 megabytes of RAM decoded. And we can see here that the values here are primarily the 0F range, which is the system ROM area at the top of the 1 megabyte of address space. So you can see the bus address latch enable basically latches these signals. And we can see that we're getting the ROM output enable is varying with the memory read signal here. And that the ROM, because we're accessing this area of address space continuously, then the ROM signal is actually enabled the whole time. And then the output buffers, we can see, pretty much match the ROM1 output enable as well. So when I first did this, these values were all not changing at all, and that was because a programmable logic device had not been programmed. So that's programmed and that's working fine. Let's go and have a look at the other signals now. So again, we can see that there's an initial about 350 milliseconds where reset is held high, so this resets the processor, and then when we come out of reset, we can see that all our signals change for a while and then everything goes quiet again. So this should be when the CPU is going into halt. So we'll go and check that in a few minutes. Let's zoom in first of all. So what we can see here, the SD8 has the least significant byte and most significant byte values here. And we can see here, this is the bottom 8 bits of the address line. So when we're actually at the reset address, which is FF0, we can see that in fact we're reading EA00, F000, F0FF. And if we go back to the listing that we had, so if we check this, this is the reason why I swapped the byte order around here, so it actually matches the listing here. So you can see that we've got EA00, EA00, F000, and then in fact we've got F0 and it goes down onto the next line with the FF. So it's read that particular code there, so that looks okay. Then what we'd expect it to do is to jump to our test code, which is going to start here. So this, we would expect the address to jump down to 00. We should have B800. So let's see if that's what we get here. You can also see down the bottom here that the decoding of these control signals shows us 04. This means is actually reading code. So we can see here now, we just bring the listing back. But now we've got 00, we have B800, B800, then we've got F0BB, F0BB, then 4 zeros, ATD8. This looks like that's correct. And then we come down to this instruction here. This is where we're actually reading the data. So we're actually reading the data indexed by the DI index register. We're just reading 1 byte of that. Now what we'd expect is we would see the status here of 06 when we're doing a memory read. And what we'll find is that 3E8A1D, so if we can find that, 3E8A1D, then after it there's a 47 as well. There's a bit of a gap between the instruction being read there. We can see then that we actually read the data here. So we found a timing marker here. And if we do it for the memory read start and the memory read finish, so what we can see here is we are reading the byte from the 00. So this will probably be at the very top of the EEPROM that we looked at the beginning. And we can see that the value that we're reading here is 00 and then 01. The first byte we're reading is 00. We then look, we're then executing the code again, and then we're reading the next byte. So you can see now that for 01 we're actually reading the 01 from there. And because this is set at 16-bit access, then in fact we're reading effectively the same data there, but the processor will actually be looking at this byte rather than this byte. So I'll just go off and mark up the rest of those, and we'll speed that up, and we'll come back and have a look after in a minute. So you can see now we're reading 03, and we'll be reading the byte there. So this is the most significant byte of the 16 bits there. Then for 4, we're reading 04 there. Then for 05, we're reading the most significant byte there. So you can see that this appears to be working, and in fact it's going all the way through a lot of addresses. So we can see that our address lines are cycling through 255 values, going back to 0. And in fact, at the end here, you can see one of the last reads we have here. So the address is FF, and in fact, the most significant byte is FF. Now, in fact, after we've done this, if we go back to our code, once we've read the last FF, then in fact, we'd expect at address 14, we should have F4, and that should then cause the processor to halt. So in fact, we then got the address 14, and in fact, the first byte there is F4. And in fact, if we then zoom out a little bit, you can see that in fact, the control lines here goes to 05, and in fact, it goes to 05, and the processor is then halted. So you can see our status 05 means it's halted. If we decoded some of these byte enable signals, we'd be able to tell the difference between a halt, which is an instruction executed in the code, and whether or not the processor has been shut down due to some sort of exception. Now I'm just going to make one more set of timing markers, so I just want to see how long this actually took. So if we add one more timing marker, so H is going to go at the beginning. So really from when we started to read the first data there, and then we'll put the end when it changed to halt. Okay, so I'll just do it there. So we can see that in fact, for this test to run through the 60,000 values here was about 414 milliseconds. So what I'm going to be doing now is having a look at a slightly different program, and we're actually going to try 2 different ways of accessing the data. We're going to use 8-bit reads like we've been doing here, and we've seen that in fact when we do an 8-bit read, the data which is read is the same, but the processor will be looking at either the most significant byte or the least significant byte. But we're also going to then try to do 16-bit reads and then see if that's any faster. We'd expect it to be obviously probably twice as fast. So now we'll take a look at our other test program. So this is very similar. We pack the first 60K with ascending bytes. But now, rather than using a programmatic loop, what we're going to do now is to use this CX as the loop count and use the rep load string byte value. This uses a data segment in the SI index register. So we clear that. This will then read 60k of all the values, and it will do it in a very tight loop. We then got a couple of these jumps. So the 386 prefetches quite a lot of instructions after the current instruction, and so this jump +2 basically prevents that prefetch from working. And what should happen is once this has finished, then we should then be able to pick up the no operations. So that's 90 hexadecimal before we do the next loop. So we've got two loops here. One does bytes and the other does words. And we do it for half the number of loops because obviously this one's going to be going up in 2s. And we also have cleared the direction so that hopefully it should be going up incrementing rather than decrementing. Then once those two tests are finished, then we'll get the halt again as well. So I've already assembled that and we've split it into our two files, so the even and the odd. So we just need to program that now. This is the even one. Make sure it is in the programmer in the correct orientation. Just read it first of all. So you can see this is the even one. They got 0002. We'll just load the even file, program it, put it back in, and the odd EEPROM. See, this has got the odd bytes. Put that back in. Now I've got the logic analyzer set up, ready to go, so we just need to turn on the power. Okay, so I'll now switch over to look at the output from that. So you can see here we have the about 350 milliseconds for the reset, and then this period here is about 138 milliseconds in total, so that's two loops we have there. So it's obviously a lot faster, and we don't really need to go into this much further. It all seems to be working okay there. So this other one really is going to be the interesting one. So again, we can see the reset period. We just go to the listing. You can see here we've got the EA00, EA00, F0, F0FF, F0, F0FF. Now we have the B800, B800, and then the F3AC is where we start the loop. You can see F3AC. So this is where the loop's actually started, and because we've got these jumps, this should actually stop it from doing some of the prefetching all of these no operation codes. In fact, if we look here, you can see this is where the reads have started. So I'm just going to put some timing markers here. So this is address 0 is read 0, address 1 reads 1, address 2 reads 2, address 3 reads 3. So this is reading 1 byte at a time, even though the data does not actually change. Now I can see here that at the end of all of these reads, so we have FF here, and the end of that read there is going to be here. So the 60k reads is now 92 milliseconds now. That isn't in a code loop. We can't actually do very much with the data, but it just shows that that loop is quite a bit tighter. And then if we look back at our code here, you can see that we've got EB00, EB00. So this jump +2 just stops some of the prefetch mechanism from working. So we're actually looking for 8 no operation codes together. What you can see here is you kind of get the EB00, then a couple of no ops, EB00, a couple of no ops. It's only really here where we get the 8 no ops. So 1 there, 2, 2, 2, and 1 there. Then 3, 1 is the first byte of the next loop. So you can see there 3, 1 is clearing our index register again. And then the F3AD is where we'd expect the load word to occur. Then F4 is our halt. So the first read of the word loop is here. You can see here that it is actually reading a bit of code there, but then from then on, we've actually just got the read. So you can see that address 0 is reading 0 and 1, address 2 is reading 0 and 3, address 4 is 4 and 5. So you can see that it's working at least twice as fast. At the very end here, when we see FF, so you can see the FE is read where we've got FEFF. Then we go into the halt here, which is where this changes to 5. You can see here that the decode of the 5 is just not being shown on the screen there. So we'll just do the end there. What we can see now is that the byte reading is 92 milliseconds and the word reading is 46 milliseconds. So it's twice as fast because we don't have to keep rereading the same 16-bit value each time. So that would indicate that things appear to be working okay. So we're able to read data from the ROM okay, and we've managed to test out both the 8-bit and the 16-bit reading there. So now we've been able to check out that our data buffers, latches, address buffers, latches, and our system address SA0 to SA19 and our latchable address 17 to 23 all appear to be working. We've got our ROM address decoder working and our read-only EEPROM here. So that all seems to be working for the moment. I'm sure there will still be a few issues we need to sort out when we start to add the 32-bit memory card here. So that's what we're going to be doing in future videos. We're going to be adding 4 512K static RAM chips in a 32-bit wide memory card, and that's probably going to take a number of videos to get that all working because it's quite a complicated part of the original COMPAQ DeskPro 386 PC. So I've been able to get our very simple test programs to prove that we're able to read the data out of the ROM so we can boot off the reset area of code. Our test programs then reading through the whole 64K of our two 32K ROMs. They're interleaved between even and odd bytes, and that all seems to be working properly. What that should mean now is that we're free to add the 32-bit memory card. I think what I might just do before we do that, I will add a power on self-test port. So the power on self-test port, or post port it was known, used to be a fairly simple ISA bus card you could put into a PC, and it would actually show you the last successful power on self-test code or post code, quite often on an LED display. Now, because we're using logic analyzers here, I can just actually plug the logic analyzer into the output of that port. So I think perhaps what I'll do in the next video, do a fairly short, simple one, where we'll add our power on self-test port and perhaps modify our test program here to output the bytes that it's been reading from the ROM actually to the post port, because we're going to need the power on self-test port when we come to do the memory and when we actually want to test the memory. So if you don't want to miss out on future videos, please hit subscribe. If you could hit like as well, it just helps to make the videos available to more people. If you'd like to leave comments, I do try and get back to you within a day or so. Thanks for watching.